I was given a suggestion that we do some practice problems for your physics homework this week. So if you take a look at your text and find the problem section, number 2 says, it is weigh-in time for the local under 85 kilogram rugby team. The bathroom scale used to assess eligibility can be described by Hooke's law and is depressed 0.75 centimeters by its maximum load of 120 kilograms. So we have two questions here. What is the spring's effective springs constant? And B, is the player eligible based on certain information? So in the problem itself, it talks about Hooke's law. So Hooke's law is force equals K times X. Now force, as we've talked about before, is a push or a pull. In this case, pull because of gravity. K is the constant for that spring, and X is how far it has moved. And so since force is ma, here because of gravity, we have 120 kilograms is the maximum it can hold. 9.8 meters per second squared is g. And that is equal to k times 0.0075 meters. Now you notice we converted centimeters to meters. That's very important in all of our functions. And if we actually solve for k, you'll get a spring constant that's very, very large, 156,800 newtons per meter. So we're going to use this information in question B. The player still uses the scale that's based on Hooke's law, but the player has different information. So in this particular case, we don't know what the mass is, but we know gravity still applies. We now know 156,800 newtons per meter is the K value, and the distance is 0.0048 meters. Again, convert centimeters to meters. We find out that the mass is 76.8 kilograms, and is he eligible? Absolutely. The next problem that we're going to do is number 9. It says find the frequency of a tuning fork that takes 2.5 times 10 to the negative 3 seconds to complete one oscillation. Now, what's given to you, the time to complete one oscillation, is the period. We're asking to find the frequency. Now, the relationship of frequency and period is that they're inverses. So the period is 2.5 times 10 to the negative 3, and that's 1 over f. So if we solve for f, we get 1 divided by the period, which gives us a frequency of 400 hertz. The next problem we have is number 14. If the spring constant of a simple harmonic oscillator is doubled, by what factor will the mass of the system need to change in order for the frequency of the motion to remain the same? So we're changing one concept and we're seeing the system stay the same, so we're going to have to make a change to the system. Now, in a simple harmonic oscillator, we use a spring and a mass of some sort of force component. Here, we're going to be using gravity. The period of this oscillator is equal to 2 times the square root of the mass divided by the spring constant. And you can see that formula on the left side of the screen. So now we have to think, if that's what the period is, we now have to take a look at what the frequency is. So we actually do the inverse. And the inverse is you flip everything. So the frequency is 1 over the period. So 2 pi becomes 1 over 2 pi. M over K becomes K over M. Now, these variables, frequency is F, M is the mass, and K is the spring constant. So now we take a look at this formula, and although we don't have numbers, we can actually take a look at the question itself. It says if a spring constant of a simple harmonic oscillator is doubled, by what factor do we need to adjust the mass? Well, it's fairly obvious here that K is under the square root. So if I put a 2 next to the K, I would need to put a 2 next to the mass so they canceled and nothing would change. So again, notice that under the square root, you double the K. To maintain the same frequency, you would double the mass. The next problem we're going to do is number 22. What is the length of a pendulum that has a period of 0.5 seconds? Now, we need to know how a pendulum works with regard to length. Well, those things are described here in this formula. The period is equal to 2 pi times the square root of the length of the pendulum divided by gravity. So gravity does affect how fast a pendulum operates. In this particular case, we've been asked to find the length, so we'll solve for L. So if we divide the period by 2 pi, we would get L over G, square root of L over G. So we square both sides, and we get L is the period squared times G divided by 2 pi, quantity squared, and we get a length of 6.2 centimeters. Now, if you do this on your calculator, you'll notice you'll get 0.062. That's in meters because, again, gravity's in meters, so we will be using that. The next problem is number 30. We're going to be using a pendulum once again. A says, what is the effect of a pendulum on the period of a pendulum if you double its length? B, what is the effect of the period of the pendulum if you decrease its length by 5%? Now, the process of solving both of these is exactly the same. You just have different numbers. So let's do A first. By taking a look again, the period of pendulum is 2 pi multiplied by the square root of L over G. So here's how it works. If you double the length under the square root, then the square root of 2 is 1.14. So the answer is 1.14 times the period. For B, if you decrease the length by 5%, that means 95% of the length is left. So you take the square root of 95 and you find the answer is 0.975 times the period. The next problem we're going to do is number 51. Scouts at a camp shake a rope bridge that they have just crossed and observe the wave crest to be 8 meters apart. If they shake the bridge twice per second, what's the propagation speed of the waves? Well, the relationship between velocity and wavelength and frequency is given by this formula. Velocity equals wavelength times frequency. So, the propagation speed of the waves is what we're looking for, and we know that the wave crests are 8 meters apart. That's the wavelength. We multiply it by 2 hertz because if they shake the bridge twice per second, that's 2 hertz, you multiply those two together and you find the value of 16 meters per second.